Sit on your couch the way you actually sit when nobody is watching. Slide your hips forward. Let the lower back round. Let the shoulders fall toward the knees. Hold it. Feel where the pressure has landed. The pelvis tucked under. The spine curled into a single long C. The diaphragm folded down onto the stomach. That is the position. I want to tell you what is happening inside it. 47 minutes is not a long time. It is 1/2 hour show with the advertisements. It is shorter than most people's commute. And in that span, a sequence of mechanical and chemical events unfolds inside you that you cannot feel because your nervous system was not built to feel them. So I am going to describe them for you. One layer at a time. Run your hand up the back of your neck and keep going. You can feel the bumps under the skin. Those are the spinous processes, the back tips of the vertebrae, the only part of the bone you can touch from the outside. There are 24 of them between your skull and your pelvis, 7 in the neck, 12 attached to your ribs, 5 in the lower back. Between every pair there is a disc, a ring of tough fiber wrapped around a center of gel. The fiber is called the annulus fibrosus, which is a fancy way of saying ring of fibers. The gel is called the nucleus pulposus, which means pulpy nucleus. The gel is roughly 80% water. Remember that. Everything else follows from that. Inside the column of vertebrae runs the spinal cord, suspended in cerebrospinal fluid, wrapped in 3 layers of membrane. Running alongside the bone, attached vertebra by vertebra like the guy wires holding up a radio tower, are the small deep muscles, called the multifidi. There are dozens of them. Each one spans only 2 to 4 segments. They are the spine's stabilizers, the muscles that do the moment-by-moment job of holding the column steady. Above them, the long ropes of the erector spinae, running the full length of your back. In front of the spine, threading down from your last rib through the bowl of your pelvis to the inner thigh, runs the psoas, the largest hip flexor in your body. Behind your pelvis, packed against the back of the hip and inserting into the side of the thigh, is the gluteus maximus. It is the biggest muscle you own. That is the architecture. That is what is doing the work right now. And that is what is about to change. Start with the disc. The disc is a hydraulic cushion. Under load, it behaves like a small inflated tire pressed between 2 metal plates. When the pressure on it goes up, the fluid inside has to do something. It has to spread. It has to push outward against the walls of the annulus, or it has to leave the disc entirely through the only available exit, the cartilage end plates at the top and bottom, which are porous like a kitchen sponge. Now, the pressure inside the disc when you stand upright was measured directly. Alf Nachemson and Gösta Elfström at the Karolinska Institute in Sweden surgically implanted pressure transducers into the lumbar discs of living human volunteers. This was the 1960s and the early 1970s. They did the thing nobody else had done. They took the pressure reading from inside the working disc in a person who was standing, sitting, bending, lifting. They published the results. They became the foundation of spinal biomechanics. Here is what they found. Standing upright, the pressure inside the third lumbar disc was roughly 100 kilopascals. Sit down on a chair with the back upright, and the pressure rises to 140. That is 40% more pressure, just from changing position. Now slouch forward, let the lower back round, let the weight of the torso fall onto the front edge of the discs, and the reading climbs to nearly 200 kilopascals, nearly doubled. Now hold that pressure for 47 minutes. The nucleus is 80% water. Water does not compress. So under sustained pressure, the water has to go somewhere. It diffuses out, slowly through the cartilage end plates into the spongy bone of the vertebra above and below. The disc gets thinner. The space between the vertebrae shrinks. The annulus, the ring of fiber that was holding the water in, no longer has the internal pressure it needs to stay tight. It begins to bulge outward. Over the course of a normal sedentary day, the average adult loses between 1 and 2 centimeters of height. That is roughly 3/4 of an inch. You are taller in the morning than you are at night. The difference is water that left your discs. That part is not metaphor. You could measure it with a tape measure. When you stand up after a long sit, the discs do not immediately reabsorb the water. The rehydration takes hours. Most of it happens overnight, when you lie flat and the pressure drops to about a quarter of standing values. That is why your back is the most vulnerable to injury first thing in the morning, while the discs are still swollen with water but the surrounding tissues have not yet warmed up. There is a sweet spot of fragility, just after you wake. Lift something heavy in that window, and you will know. And while the water is leaving the disc, something else is happening on the backside of your spine, something the discs themselves cannot tell you about. There is a chain of ligaments running down the rear of your spine, the supraspinous, the interspinous, the ligamentum flavum, the posterior longitudinal. They connect the vertebrae the way a chain of elastic bands connects the segments of a wooden snake. When you sit slouched, those ligaments are stretched. They are bearing the load that the muscles have stopped bearing. And ligaments, like all collagen tissues, are viscoelastic. That is a 4-syllable word for a simple idea. They behave partly like elastic, snap back when released, and partly like putty, deform under sustained load and stay deformed for a while. Hold a ligament in stretch for 20 minutes and it will not snap back to its original length the moment you release it. It will be longer. It will be looser. It will recover over time, but the recovery is slow. Stuart McGill at the University of Waterloo measured this. In a series of experiments through the 1980s, McGill placed anesthetized cats into positions of full spinal flexion for 20 minutes. Then he released them and measured how long it took for the ligaments to return to their pre-flexion tension. The answer was 7 hours. 7 hours of unloaded recovery for 20 minutes of sustained stretch. The reason this matters is not just structural, it is sensory. The ligaments of the spine are not just passive cables, they are sensors. Woven into their fibers are stretch receptors, small mechanically activated nerve endings that report position and tension back to the spinal cord. Proprioception, the sense of where your body is in space without looking. When the ligaments creep, the stretch receptors stop firing accurately. The reflex arc that would normally pull you out of a dangerous position before you consciously felt the danger is dampened. You are losing the spine's own alarm system. The protective signal is muffled, and you do not know it is muffled, because the silence of an alarm is not something you notice. You only notice it when it fails to go off. The ligaments are going slack. That should be a cue for the muscles to take over the stabilizing job. The muscles do not take over. Put surface electromyography electrodes, the little adhesive pads that read electrical activity through the skin, over the lower erector spinae and the multifidi of a person sitting slouched. The signal is nearly flat. The muscles are electrically silent. Manohar Panjabi at Yale, in his early work on what he called the neutral zone of the spine, was among the first to characterize this. The spine has a small range of motion in which the passive structures, the discs, the ligaments, the joint capsules, provide almost no resistance. Inside that zone, stability depends entirely on muscle. And in sustained flexion, the body decides that the passive structures will bear the load, so it switches off the muscular contribution. This is called the flexion-relaxation phenomenon. Energetically, it makes sense. Muscles burn calories. Calories are expensive. If the ligaments will hold the position for free, the brain shuts the muscles down. Mechanically, it is the worst possible decision. Because the discs are losing water, and the ligaments are creeping, and the structure has handed responsibility to two systems that are deteriorating in real time. And here is the part that is harder to swallow. The multifidi do not just go quiet. Once they have been silenced for an extended period, they forget how to fire. The motor cortex, the part of the brain that recruits muscle, drops them from its active map. Researchers have shown that after a single episode of acute low back pain, the multifidi do not return to their previous activation pattern spontaneously. They have to be retrained. Deliberately. The longer they are silent, the harder the retraining gets. And fatty infiltration, actual replacement of muscle fiber with fat, visible on MRI, can be measured after sustained inactivity, not over years, over days. While the muscle is silent, something else is changing, something not in the spine, but in the chemistry of the muscle itself. Inside every skeletal muscle fiber sits an enzyme called lipoprotein lipase. People who talk about it shorten it to LPL. The enzyme hangs off the inner wall of the capillaries that thread through the muscle. Its job is straightforward. It grabs triglycerides, fat molecules, 3 fatty acid chains attached to a glycerol backbone, out of the passing blood and breaks them into individual fatty acids that the muscle can pull in and burn for fuel. Lipoprotein lipase is the doorman. It is what pulls fat out of circulation and into the tissue that can use it. Researchers working on what has come to be called inactivity physiology measured the activity of lipoprotein lipase in the soleus muscle, the long flat muscle behind your calf, the one you cannot see in the mirror, under different conditions. When the soleus contracts, even at very low intensity, the enzyme is active. The doorman is at his post. When the soleus is held still, when the calf is at rest for a sustained period, the activity collapses. It drops by more than 90% within hours. Not a slowdown, a near total shutdown. The consequence is that the fat from the meal you ate before you sat down, the triglycerides circulating in your blood, are no longer being pulled into the muscle. They keep going around. Blood triglycerides climb. The high-density lipoprotein, the HDL, the type that scavenges fat from the bloodstream and is generally considered the protective cholesterol, drops measurably over hours of inactivity. The lipid profile shifts in the bad direction. This is not a slow process. It does not wait for hours. It begins within minutes of the calf going still and reaches near baseline silence within 1 to 4 hours. And it is not driven by lack of exercise in some general sense. It is driven by the specific absence of low-intensity contraction in the postural muscles. A person who sits all day and then runs for an hour does not undo the silence. They suppress it for the duration of the run, and it returns the moment they sit again. The frequency of activation matters more than the intensity. As the soleus stops working its chemistry, it also stops working its hydraulics. The soleus is sometimes called the second heart. Not because it pumps blood with the same rhythm, it does not, but because, when you walk, it squeezes the deep veins of the calf with each contraction, pushing blood back up toward the chest. There are one-way valves in those veins. Each squeeze advances the column of blood upward by 1 centimeter or 2. Over the course of 1,000 steps, the soleus moves an enormous volume of blood against gravity back toward the right side of the heart. When you sit, the squeeze stops. The valves remain in place, but no force is acting on them. Blood pools in the legs. The volume of blood returning to the heart per beat drops. The heart has less to pump. Stroke volume falls. That is the simple mechanical part. The chemical part is what concerns the artery walls. When blood flows briskly through an artery, it exerts a kind of dragging friction on the cells lining the inside of the vessel. Those cells are the endothelium, a single layer of tissue, 1 cell thick, that paves every blood vessel in your body. If you laid the endothelium of an average adult out flat, it would cover a surface area larger than a tennis court. It is the largest organ you have probably never thought about. The dragging friction is called shear stress, and shear stress is what tells the endothelium to function. It is the mechanical signal that keeps the cells producing nitric oxide, the molecule that signals the surrounding smooth muscle to relax, keeping the artery open. When the shear stress drops, the nitric oxide production drops. The artery becomes less responsive. It is less able to dilate when blood flow needs to increase. The endothelium is failing to do its job. Researchers at Indiana University placed a blood pressure cuff above a person's knee, inflated it for 5 minutes, and then measured how much the popliteal artery, the large vessel behind the knee, dilated in the seconds after release. This is a standard test of arterial responsiveness called flow-mediated dilation. After 3 hours of uninterrupted sitting in healthy young adults, the popliteal flow-mediated dilation dropped by roughly 50%, cut in half. 3 hours of stillness. And then a curious finding. When the same period of sitting was broken up with 5 minutes of walking every hour, the impairment did not occur. 5 minutes per hour was enough to preserve the endothelium, not a workout, not a regimen, just an interruption of the stillness. There is one more thing happening in your slouched position. Look at the geometry. When the spine curls into a single long C and the rib cage falls forward onto the abdomen, the diaphragm, the dome of muscle that separates your chest from your gut, the primary muscle of breathing, is compressed from below by the contents of the abdomen and from above by the falling weight of the rib cage. It cannot descend properly on the in-breath. The space available for the lungs to expand drops. By how much depends on the slouch, but reductions of 20 to 30% in functional residual capacity have been measured in healthy adults moving from upright to fully slouched seated postures. The breath gets shallower. To deliver the same amount of oxygen, it has to get faster, and a shallow, fast breath is not a neutral state. It is a signal. The brainstem reads it as a low-grade vigilance pattern, the kind of breath your body produces under mild threat. The autonomic nervous system shifts. The parasympathetic branch, which runs through the vagus nerve and governs the rest, digest, restore mode of the body, eases off. The sympathetic branch, which governs fight or flight, edges up. Heart rate variability, the millisecond to millisecond variation in beat-to-beat timing, which is one of the cleanest measures of vagal tone, drops in postures of sustained chest compression. The drop is not large, it is not catastrophic, but it is measurable, and it is sustained over the duration of the slouch. So now you can see what 47 minutes really is. It is not just rest. It is 6 things happening at once. The discs are leaking water. The ligaments are creeping into laxity. The multifidae are silent and beginning to forget. The lipoprotein lipase is shutting down in the calves. The endothelium is losing its tone, and the diaphragm is compressed and the vagus is muffled. I want to pause here, because there is a temptation, when you have laid out 6 mechanisms in sequence, to make them all sound equally strong. They are not, so let me grade them. The disc pressure measurements from Nachemson and Elfstrom, implanted transducers in living human spines, repeated across multiple subjects, replicated independently in subsequent decades. That is direct measurement. That is as solid as physiology gets. Settled. The lipoprotein lipase shutdown, direct biochemical assay in rodent and human muscle, with the cellular mechanism worked out down to the messenger RNA solid. The endothelial dysfunction from sitting, measured in dozens of laboratories with consistent results, with a clear dose response, and a reversibility demonstrated by interrupting the sitting. Robust. The ligament creep findings from McGill, strong in animal models, well grounded in the basic mechanics of collagen, partially confirmed in humans by indirect measurements of stiffness recovery. Likely correct, more thoroughly nailed down in the laboratory than in the living human in vivo. The multifidus silencing and motor forgetting. The silencing is easy to demonstrate on EMG. The longer-term consequences over a single 47-minute sit, specifically, are more inferred than directly measured. Reasonable. The autonomic shift from slouched breathing, physiologically coherent, consistent with the broader literature on respiratory influence on vagal tone, but the size of the effect over short durations in a healthy person is still being characterized. Plausible, not settled. I am not telling you they are all the same. The hierarchy matters. It tells you which interventions are likely to help, which are still hypotheses, and which sit somewhere in between. A scientist who hides the hierarchy from you is selling you something. Now I want to talk about something else. The lipoprotein lipase shutdown, the doorman who goes off duty when the calf stops moving, dropping fat clearance by 90%, operates through the same molecular pathway that one of the most heavily prescribed drug classes in the developed world targets. The drugs are called fibrates, fenofibrate, gemfibrozil. They are prescribed to people with high triglycerides and low HDL, the same lipid profile that sustained sitting produces. They work by activating a nuclear receptor in the cell, a kind of molecular switch in the nucleus, called peroxisome proliferator activated receptor alpha. People shorten it to PPAR alpha. When PPAR alpha is turned on, it walks to specific stretches of DNA and tells the cell to make more lipoprotein lipase, to put more doormen at their posts. Standing up and walking, even slowly, even briefly, activates PPAR alpha through muscle contraction. The mechanical work of the soleus triggers a calcium signal that ends, downstream, at the same nuclear receptor. The fibrate molecule activates it pharmacologically, from the outside, through the digestive system and the bloodstream. The pathway is the same. The molecular target is the same. The downstream gene activation is largely the same. The fibrate is more potent. It will produce a larger drop in triglycerides in a person who cannot walk, or who will not walk, than a 5-minute walk will produce in that same person. That is what the drug is for. That is why it exists. But there is something to notice. A common prescription for a metabolic problem, a problem you can produce in a healthy body, on demand, by sitting for 90 minutes after a meal, is a drug that activates the same nuclear receptor your soleus muscle activates for free. The pharmaceutical pathway and the postural pathway are not separate systems. They are the same system, accessed by different routes, at very different prices. I want you to picture someone specific. A man, perhaps 62, office worker for 40 years, recently retired, sitting more, not less, because the structure of the workday has been replaced by the structure of the couch. He has been told his triglycerides are high. He has been told his HDL is low. He has been put on a statin, possibly a fibrate as well. His doctor mentioned almost as an afterthought that he should try to be more active, walk more, move around. He has not been told that the lipid panel which prompted the prescription is being held in place hour by the position of his body. He has not been told that lipoprotein lipase is what he is treating, and that lipoprotein lipase responds to contraction of the soleus, and that the soleus is the small flat muscle behind his calf, and that he does not need a gym to use it. He has not been told because nobody handed him a mechanism. He was handed a pill and a brief instruction and a follow-up appointment in 3 months. The mechanism was never on the menu. My grandmother used to say, and I expect yours said something like it, "Do not sit too long, you will get stiff." When I was small, I thought this was a vague remark about old people and arthritis, the kind of thing grandmothers say. It is not. It is 6 mechanisms in a sentence. The discs are losing water. The ligaments are creeping. The deep muscles are going silent. The doorman in the calf is shutting down. The artery linings are losing their tone. The diaphragm is compressed and the breath has gone shallow. She did not know the molecular detail. She did not need to. She knew the output. She had watched it happen, in her body and in the bodies of everyone around her, for 70 years. The phrase was an empirical observation, compressed into 8 words, by a woman who had no laboratory, but had something more important, a long memory and an unsentimental eye. So, 47 minutes. The episode is almost over. Here is what to do. Stand up. Just stand. You do not need to stretch. You do not need to exercise. Walk to a window. Walk to the kitchen. Sit down again in 5 minutes if you want, but break the silence in your soleus, even briefly, even once an hour. That is what the research keeps showing. The frequency of interruption matters more than the duration of exercise. A person who sits for 10 hours and works out hard for 1 hour at the end of the day is metabolically different, and worse off, than a person who sits for 10 hours but stands and walks for 2 minutes every hour. Frequency, not intensity, not duration, frequency. Do not sit too long, you will get stiff. Stand up. Tell me, what was the longest stretch you sat through today, and did you feel any of it at the time?